I'll start off with a bit of a recap of what we did last time, and I'll start off with that the simulated world we had to kind of recap over the key concepts of value function, rewards, and cumulative rewards, right? Actually, before I'll just ask you all and see how much you all remember. Let's see. State action, state action, reward, cumulative reward. And let's put a value function and a Q function. So does anyone remember the significance of any one of these individual terms? Let's start with reward. Does anyone remember what reward was?
Cold beer at the end of the day.
What?
Cold beer at the end.
Oh no, that's cumulative rewards. If you were good throughout the day, the cumulative reward is that's cumulative. But yeah, good point. So okay. So state is the general state in which the RL environment, RL agent is acting. So if the RL agent is acting in a video game world, then the state of the video game world refers to the state. We also work with observation, which is like the portion of the state which is actually visible to the RL agent. For simple examples, they're basically the same thing, but for more complicated examples, they diverge. Action is the particular action an agent can take. If you all remember, let's actually start with this. So we had this kind of a diagram in the last meeting. We had this kind of a diagram. Do you all remember this diagram from last meeting? Does anyone remember this diagram from last meeting?
You sure?
It's incomplete. It's incomplete. There are parts of it missing. But does anyone remember this? Also in the chat. And how is this visible in the... Oh, nice. That is visible. Let's go with chat. Okay, let's see if this puts in. Hey, I can use that as a reference to check if it's all visible. Nice. Perfect. Oh, so
It's a much better marker.
yes. All right. Can anyone help me fill in this diagram as a recap for the basic principles we covered in last lecture? So I'll start off with this is the agent. This is the world. Does anyone want to give a guess at what the first thing could be? What goes from the world to the agent, or what does the agent perceive about the world? State. Yes. You've got state or so we can just call this state R, SI. So the agent, and that marks the first bit. The agent perceives the state or perceives an observation of the world. And based on that, the agent does something to influence the world. What does the agent do to influence the world? Yes, that's the action. The agent takes an action. So if you're thinking of, okay, the agent takes an action. And when the agent takes an action in the world is typically changed and the world responds. What does the world respond with? With a reward. So that responds with a reward, a single R. Okay. And when the world is after the world responds with a reward, the world is changed. There is a new observation to be made. And that's like S plus 1. So we start with the initial state. Based on the initial state, the agent takes an action. That action influences the world and changes something in the world. Based on that change, the agent receives a reward, which could also be a negative reward in the case of a punishment. And the agent can use that reward as feedback on improving its own learning algorithm, or rather, on improving its policy. Okay. Oh, that's another keyword, policy. So to start off, we kind of finish a recap. So we kind of covered action. Does anyone want to attempt an example of this? An example of this dynamic with, let's say, training a pet dog to do a trick or learning to ride a cycle. Does anyone want to attempt an example? In the chat as well. All right, everyone's probably still warming up. I'll start off with the example. Okay, so in the case of a dog learning to do a trick, you have the dog and you have the environment, and the environment is basically the environment controlled by you. Okay, so do we have Dusto? Yes, I forget it's here. So we can swap this out for that's either more a cat or a dog with. That's probably more a cat, but I'm just going to call. So you have a dog that's learning to that you're training to do a trick, and the dog sees the environment, and the environment state could be you raising your hand out. Maybe you're teaching your dog how to do the handshake trick. Okay, so the environment, the state that the dog sees is your palm raised out, and the dog may raise its own palm a little bit to kind of bring it closer to your palm. That would be the action. In response to that action, you might give it a reward of treats and compliments and encouragement, calling it the goodest boy ever. And the dog can use that as a way to realize, in the case of the state of you, the owner, having your hand raised out, doing something with its own hand yields a positive reward. And it can use that to encourage, to inform its future decisions. So the next time it might do the same thing again, you give rewards. And you have the next state where your hand is still raised out, but maybe a bit closer. The dog can use that, and this is kind of the rough cycle with how you might train a dog. So that kind of covers a recap of a reward action. And a reward is like the instantaneous positive or negative feedback response you get from the world. That's instantaneous. Reward is kind of like hard linked to the action. Let's look at the next one. Does anyone remember cumulative rewards?
Is that like a future combination of rewards?
Yes, that is indeed the future culmination of rewards. Cumulative rewards is a way to consider not just what is a good action right now, but what's a good action all the way into the future. If you'll remember what we did last time, we had an example. Last time we had an example world which went something like there was a pitfall over here, and there was a slippery slope over here, and there was a star and goal at the end. And so we had a kind of rough environment like this. And when we looked at rewards, the rewards would basically just tell us to keep going right regardless. But a consideration of cumulative rewards helped us recognize that the pitfall is something to be avoided, because going into the pitfall will send us back, and then we have a few steps where there are no rewards. Or a more empirical way to think of reward is if you have a series of actions, like you've got state one, and then action one, and then reward one, and then state two, action two, reward two, state three, action three, reward three. If you have a series of state, action, reward pairs like this, the reward is the individual reward you get. The cumulative reward is going to be R1 plus R2 plus R3 plus R4, and so on. Is that right? Yes. You're thinking of something, aren't you? Is this right? Based on what we did last time?
We added like a scalar to it.
Yes, we added a scalar. That's right. We added a gamma scalar. The gamma scalar is the discounting factor. So it's instead of like this, the cumulative reward was calculated something like this. So first reward plus the second reward times gamma, third reward times gamma squared, fourth reward times gamma cubed. Okay.
Why is it this way? Why do we need this powers?
Yes, okay. So why do we need this power? Okay, if you're going to think of, if you're in a state, okay, state I, and you have two possible actions from here. Action, well, let's call it action A and action B, okay? And based on what you know, action A is going to put you on a trajectory where your reward looks like you initially get a reward of 1, then no reward, then reward of 1, then no reward, then reward of 1, then no reward, and so on. And action B puts you on a trajectory where you get a reward of 1, 1, 1, 1, 1, and so on. That's, oh, so, okay, this is your continuous action. The objective of the cumulative reward is to help us conceptualize rewards, all the rewards in the future, into a single number. So it's kind of taking a sum of everything. But if we simply take a raw sum of everything, action A part and action B part technically look the same, where they all kind of become infinity. And you can't really make sense of infinity when you're making comparisons. You can't really compare them. So using the gamma function is kind of like a trick where there are a few different places you can look for inspiration for this gamma function. One place is in like economic studies, where the idea is getting a big reward in the future is similar to getting a small reward right now. Or if you are going to forego a reward right now, it needs to be at the cost of a big reward in the future. So it might be something like this. If you want to make a comparison of these two statements, how do you?
Wait, which one is gamma one, or which one is the first reward?
Oh, yeah, okay. So this is trajectory from action A. This is trajectory from action B.
Okay.
This is the first reward on action B, A, second reward, third reward, fourth reward.
Is gamma less or greater than 1?
There is no gamma over here.
I know, but in the formula, gamma is less or greater than 1?
Less.
Less than 1.
Gamma is always
So
less.
it becomes smaller as we.
It becomes smaller as we're going.
So therefore, we emphasize future rewards less than the current rewards. Or sorry, we emphasize short-term rewards more than long-term rewards.
Yes.
And isn't it something opposite to what you just said we want to do?
Aha. So no, what we are doing is we are stating that the rewards right now are more valuable than rewards in the future.
Yes,
But the rewards in the future still have value.
that's true.
So-
But they're less valuable.
Inherently less valuable, yes. So unless something really special is happening in the future, we don't want to sacrifice the current reward.
Okay, sure.
It's a way. Now, this is a trade-off. How valuable does a future reward need to be to give up on the current reward? That's a trade-off that needs to be defined. Gamma is a way we can control and parameterize this trade-off.
Oh, I see.
So let's kind of look at that. So we have these two trajectories, and we need to make a comparison on which action should we take. Action A will give us a reward that looks like this. Action B will give us a reward that looks like this. Okay. So let's start with gamma. Do we also have another marker color?
In a colorful?
Yeah. For now, I'll just start off with this. Okay. So let's say if gamma equals 0.1. Let's start with gamma of 0.1. And let's look at what this entire reward trajectory becomes. It will become 1 plus 0 plus 0.01 plus 0 plus 0.0001.
But you still have infinity at the end. That's gonna
Aha.
cause it to become infinity.
Yes, you do not have infinity at the end right now, because this is a geometric progression sum.
Sure.
And a geometric progression sum does converge to a specific value. In this case, it's going to converge to, what's the geometric formula? It's 1/1 minus r, I think. Yeah, 1/1 minus r. So over here, we started with 1 plus, and the rate is 0.01. So that's going to be 1/1 minus 0.01, which is equal to 1 over 0.99. And just going to look at a calculator for this. 1 divided by 0.99. So this actually converges to 1.01. 1.0101, repeating. So because the gamma function is kind of constantly making the future rewards smaller and smaller, the infinite sum will actually converge to a specific value. And now we can do the exact same calculation for the bottom one. And we're using the same gamma equals that. It's going to be 0 plus 0.1 plus 0.01 plus 0.001 and all the way in the future. And it will start off with the whole 1 over 1 minus 0.1 is going to be, that's for the start, sum 1. 0.9 is equal to 1 divided by 0.9 is going to be equal to 1.11. Okay, so if we are comparing this trajectory and if we are comparing this trajectory, we have a way to make the comparison as 0.1111, that the cumulative reward from this point is going to be 1.00101. Over here is going to be 0.111 because the first value is 1. So even though technically this is a continuous series of ones, because the first value is not 1, it's not as valuable as the entire top series. And so here's using a gamma of 0.1, we get a value like this. It's gamma of 0.1 is kind of giving a reward, giving a more preference to the immediate instant reward. Let's try the same exercise with a gamma of 0.9. Okay, so theoretically, gamma is how we parameterize how much value we want to give to future rewards. If future rewards are very valuable, we make gamma high. If we want to be less future thinking and more present thinking, we make the gamma value small. Okay, so let's kind of redo that. It's going to be, okay, that. I can do even less mental math over here with multiplication of 0.9. So you just can shout out the values as they come in. So it's going to be 1 plus 0 plus 0.81 plus 0 plus what 0.81 squared?
Oh. It's 0.6561.
0.06
6561.
6561.
No, 6561.
0.06561.
No, it's no for 0 and
Oh,
yes.
no for
Yeah, other than that, it's good.
Okay, and so on. What we're getting here is 0. Okay, so that's going to basically be, I'm just going to work out the calculation over here. Camera's not going to see it, but the rest of everyone can see it. It's 1 over 1 minus 0.81 is equal to
Yes.
1 minus 0.81. That's 1 over 0.91.
Over 0.19.
19.
Big number.
Yeah. That's right. That makes sense. 5.263. So this sums up to 5.263. thing to note, 5.263 is bigger than 1.001, which makes sense because initially we were giving very less value to the future rewards. With gamma of 0.9, we are giving much more value to the future rewards. So there is a much heavier contribution, and so the value is much higher. Let's repeat the exact same thing for the bottom series. We're going to start off at 0 plus 0.9 plus 0.81 plus 9 ones are 9, 8 and 9 is 72, 0.72 plus. Is this making sense, by the way? So just quick check-in. How many of you feel even a little bit lost? How many of you feel like you're keeping up? Keeping up. Nice.
Wait, I have a question.
Absolutely. Yes.
So, like, this is making sense, like, what you're doing here, but I wasn't here for the last session, so like, what is the context of this? What are we taking a look at right now? What is this for?
Oh, yes. What is this for? Okay. So in the last class, we had a game. Like we actually ran through and simulated a game where there is this kind of a map where you have cells, top cell, bottom cell, top cell, bottom cell, and there are stars at the end. And we played as agents within this map, trying to navigate our way to the star. And then what we have done is we kind of made a rule that for every time you go to a new column, you get a new reward of 1 point.
Okay.
But it's like when you explore a column for the first time. And then we showed an example of someone who already knows the full map and knows that there's a star. How will that person work? That person will just navigate straight away because they know there's a goal.
Yeah.
But if someone does not know that there is a goal at the end and someone is going off only the individual rewards, we showed that if you follow only individual rewards, you're going to keep going right, but you're still going to be susceptible to some mistakes. And then we introduced the concept of cumulative rewards, what we're doing right now.
Okay.
And then we showed that instead of chasing the individual reward of every column, if we create an estimate of a cumulative reward and try to chase that estimate, then we can make better decisions. Specifically, there was a pitfall trap over here where chasing rewards did not help us avoid the pitfall. But with the same kind of reward structure, chasing cumulative reward helped us avoid the pitfall because in the pitfall scenario, the cumulative rewards were much less because you got less rewards in the future. And so that distinction between reward and cumulative reward was like a big, I wouldn't say game changer, but yeah, I would say game changer. Yeah. So right now we're kind of just doing a recap of that, but in a more mathematical way.
So there are you calculating like a cumulative reward based on the omega and how it changes?
Based on the gamma and how it changes.
Yeah.
Yes. And so a key concept of cumulative reward was the gamma parameter. And we are showing that how if the gamma parameter is high, the cumulative reward is a more forward-thinking cumulative reward. It considers the future better. But if it's a low value, it considers the future less better. And so, yeah, the red ones are gamma of 0.1 and the black ones are gamma of 0.9. Cool.
Yeah, that makes sense. That's cool.
Nice. And we're just at the final piece. Now we're going to see. Oh, anyone else have any other questions?
Someone in chat.
Yes, someone in the chat. So is gamma a sort of activation function? Okay, no. Gamma is not an activation function. Activation function is a concept in the neural network, and we will hopefully come to it today. Gamma over here is a scalar parameter. It's a scalar parameter in the cumulative reward function. All right, good. Nice. Glad to see it makes sense and it's helpful. All right, let's wrap this up. So cumulative reward over here, it's going to be 1 over 1 minus 0.9 is equal to 1 over 0.1 is equal to 10, and we do a minus. This one is going to be a 9. All right. So the cumulative reward using gamma of 0.9 over here turns out to be 9. So look at this. The rewards over here are 1, 0, 1, 0, 1, 0, and all the way through. The rewards over here starts off with 0, but then goes on to be continuous ones. Okay. If you're going to be very if you're working on a policy that's thinking very much about the present and what reward you can get right now, this might look like the better option because it starts off with a reward. Over here, there's no reward to start off with. So if you're simply chasing rewards as it is, you might end up going here. The same with if you're more concerned about present rewards, you might go over here. A low gamma of 0.1 leads you to think action A is the better part because it has a higher cumulative reward. 1.01, so and so. But if you increase your gamma and start to try to think more forward thinking, try to give a higher consideration to future rewards, then what it turns out is because these ones are kind of dropping every intermediate one, the cumulative reward is only 5 compared to a cumulative reward of 9. And the cumulative reward of 9 is like, even though the current action, the first reward is going to be 0, a gamma of 0.9 gives enough consideration to the future rewards to recognize that the future potential over here is better than the future potential here. Is that like how's that feeling about gamma right now? That kind of concludes the brief description of gamma and also concludes a brief description of, I say brief, but this wasn't brief, was it? Okay. So that's rewards and gamma. How's everyone feeling right now so far? This is kind of like a good checkpoint to actually stop and reevaluate everything before we move on. Looking good? Looking good, good. How's the chat? How's the chat feeling over here? Oh yeah. Here's a bunch of equal signs to make it clear. All right, what is the next step in this thing we were going to do? Yeah, okay, that's the recap. Now, 3. We're going to look at the different RL types. Okay. Final thing about these things. Does anyone want to give out a shout out to what we, Q, and policy are?
V is like how good the state is.
Mm-hmm.
Q is like how good would the state be given action.
Yes. So if cumulative rewards are a way to kind of capture value, V is an estimate of what the cumulative rewards from a particular state will be. Q is a function that will estimate how good the cumulative rewards from a state given an action will be. So a more complete picture is going to be V of S and Q of S, comma A. What about policy? So policy is the function that makes a decision given the current state what action to take. It's often denoted as a pi. So it's often kind of noted as pi of S. And that leads to an action. That's kind of how it is. This leads to a prediction of cumulative reward. This is a prediction of cumulative reward as well. Okay. Let's kind of clear all of this out and start off with the different types of. Oh, did anyone want to take a snapshot or something like this? We can just draw the whole thing again, or it'll be an exercise to work out that function on your own. Okay, so that's, I guess, enough of a little bit of the, that's, I guess, like a bit of theory. What I was thinking of next is just to kind of make you all familiar with names you're going to see in reinforcement learning. Okay, so RL is a technique that has been around for a while. And there have been multiple different approaches to actually doing RL. What I showed you earlier was like some of the basic concepts and principles. Those concepts can be played around with and put together in a few different ways to come up with different algorithms. All right. So you have reinforcement learning. And then two ways to look at reinforcement learning are model-free and model-based. Model-free and model-based. Does anyone want to make a guess at what they mean? And this is honestly just throw away guesses based on the name.
One uses a model and one doesn't.
Yes, the key part is a model of what? The answer is model-based reinforcement learning strategies create a model of the environment. So you can think when you're playing chess with a friend, you can in your head conceptualize moving a pawn in a way and then imagining a response from your opponent and then making the next move. In fact, when you're doing this, aren't you basically running a simulation of the chess game in your head? And then when you want to make a decision, you run a few hypothetical simulations in your head and use that to make a decision in real life. Does that kind of make sense? That kind of a strategy is like a model-based strategy. You kind of run a simulation of the entire thing and you use your mental simulation to make better decisions. Either you can use your mental simulation to think about the game and think about what strategies are good. So after a game is done, if you won or lost, you can kind of replay a game in your head and try out simulating different strategies. That's one way. That's a model-based. Now, if you want to think about model-free, think about riding a cycle. When you're riding a cycle, you are not, or when you're learning to ride a cycle, you basically kind of just try to learn the right combination of muscle pulls and muscle twitches, which will help you ride the cycle. You don't run a simulation. Actually, some people might, but you wouldn't normally run a simulation in your head and try to predict and try to practice with a simulation in your head of how to tweak your muscles to ride a cycle. You just attempt it on the physical thing and practice riding on the physical cycle, and that's it. Does that make sense? So in model-based methods, you're running a simulation of the environment within your algorithm. Now, if that simulation is a good simulation, it can be very helpful. But oftentimes, it's not easy to get a good simulation because you got to model a lot of physical dynamics. You got to work out physics principles and stuff like that. And that can get complicated. Also, you might even know what the actual dynamics are. So you might not know enough to run a simulation. Now let's look at within model free, there are kind of two approaches. One is value learning, and I think, am I spelling that right? Yeah. Policy learning. Also, just to be clear, this isn't an exhaustive list of everything. This isn't like an exhaustive relation tree. It's just some relations which I find interesting, and I'm going to highlight them. And okay, so value learning and policy learning. So based on what you know over here, you might actually already be able to predict a little bit about this. What's the difference between value learning and policy learning? The basic gist is, you remember how these three things are basically functions and we normally approximate them using neural networks? So and so these three things are approximately using neural networks: the value function, the Q function, and the policy function. In value learning, we are focused with learning approximations for the V function and Q function. And then once we have that, The policy is determined by taking the action which leads to most value. Value function is about which state, rather, what is the value of a value learning methods concern themselves with learning what is the value of a state. So if you, what is the value of a state? And then when you want to figure out a policy of what action to take, you literally do a search. If I take this action, that's going to be the next state. And if I take that action, another action is going to be the next state. Now I have this state and that state. What's the value of this one? What's the value of that one? Which one has a better value? This one's got a better value, so I take the action that leads to that. You might see it's kind of an indirect convoluted way of doing it. But when we were looking at the entire simulation and when we were chasing the rewards, when we were chasing the cumulative rewards, you could kind of see this in principle. If you know the cumulative reward for every state, you can just try to take actions which will put you in states of high cumulative rewards. That's value function. Policy learning, on the other hand, concerns itself with directly learning a policy. So with value function, you only learn a neural network approximation for either V or Q, and then you do a search using V or Q for the best action. With policy learning, you learn a neural network for the policy itself. So just policy learning is all about just straight away jump to the action. So we're going to see examples of this. So if the distinction isn't entirely clear, then some examples later on will help us understand the distinction. But before that, I want to make a sense. How many of y'all are able to like make a clear distinction between value learning and policy learning? Is there like a clear in your head, it's an obvious difference? Or is this something you need to kind of strain to understand the difference of? It took me a while to like get like a clear differentiation between these two. What is the value of a state versus which action, bro? The two styles of thinking.
Definitely feels gray.
Huh?
Definitely feels a little like gray.
Yeah, it does feel a little bit gray. It does feel a little bit gray. So we will, once we come to the first example of Q learning, you will have one side with which you can contrast the hypothetical other side. And eventually we'll come to the other side. But let's look at value learning. Because right now the examples that we've done have been more value learning focused. Okay, so with value, like a really cool technique in value learning is called temporal difference learning. And temporal difference learning is a really cool algorithm, or it's a really cool algorithm or strategy. When you're implementing code, there are kind of two ways to go about it. There is the Q learning, and there is SARSA, state action reward state action. Let's kind of look at Q learning. We're going to look at an example of Q learning, and Q learning is essentially literally just learning the Q function and then just putting in different action values to see what gives us good reward and taking an action based on that. Q learning and SARSA, they basically differ in how we approximate it and how we learn the Q function. But we're just going to see that. And for the sake of clarity, I'm just going to put out a bunch of names over here and we can refer to this later on as we come across more chapters. But for now, I just going to want to put this map in front of everyone. We've got, what's your name? Active critic. And active critic. How would it go? Good, ready? Good. Proximal policy. Okay. So with policy learning, there is an active critic method and a proximal policy optimization. These are like two significant ones. There are a few more significant ones, but these are the ones I'm interested in. These are the ones I'll talk about later on in the future. And I guess the final thing is the reason I'm including model based is eventually I want to talk about Dreamer V3, which also has an element of active critic in it. Okay, so this is kind of the general map of RL I'm kind of going to be discussing. And so in the future, when I'm kind of coming up with examples, I'm going to use these as references points to each other. Okay. Right now, just out of curiosity, just based on the names, what names sound interesting to you all? This is mostly just me being curious. There's an active critic method, proximal policy, Dreamer V3. That model literally is about dreaming, and it's so cool. Q learning and SARSA. SARSA. Yeah.
Curious about SJSU.
You're curious about SARSA? Oh, nice. Okay. So SARSA is it's called state action reward state action, where the idea is you're in a state, you take an action, you get a response reward, and you get a response state. And then you look at what's the next action you're going to take, and you're going to use a combination of all of that to make a decision. The way it differs from Q learning is you got a state, you take an action, you get a response reward, and you get a response state, and you don't consider what's the action you're going to take next. With SARSA, you throw a consideration of your final action. So I will keep that in mind. So Ivy is interested in SARSA. Or at least that sounds curious. Active critic. Does anyone want to throw a guess at what the idea of active critic is? So in active critic, you have two components to the algorithm. One component, the active component, is all about learning a policy, and it's essentially trying to learn what a good policy is, and it takes help from the critic. Critic is usually the parts that kind of learn the values, and the critic part of the algorithm basically is used to make a decision on whether or not an action was good. And so if an action is good, if the critic says the action is good, the actor learns to do that action again and again. If critic says the action is bad, the actor learns to avoid doing that action in the future. Again, these are oversimplifications, and I'm just throwing out names. If you start kind of reading about RL papers and stuff, or RL blogs and something, if you read these names, you know kind of how to relate them to each other. Final thing I'll just mention about proximal policy before we move on to code demos, or rather than code demos, just cool demos. With proximal policy optimization, the idea is when you're learning, you don't want to make drastic changes in how you behave. Okay, if you're learning something and you kind of happen, if you're learning something, if you're learning a strategy, you want to improve your strategy in small incremental tweaks. The reason is if you make one massive tweak in your strategy, you don't always know how that massive tweak is going to have consequences in other places. But if you make a tiny tweak, the strategy might still feel reasonable to work with. And so proximal policy is all about how do you make sure that your tweaks are tiny tweaks, how to deliberately make tiny tweaks. I'll leave it at that. What we're going to do next is show you a bunch of demos.
Demos, I wanted to show you guys some things you can actually run on your laptops right away to get a sense of what reinforcement learning agents can solve and what kind of problems you can expect to solve on your laptops and like with some simple hardware right away. What we will want to do is we'll want to get stable baselines for some of the demos. Stable baselines, 3 extras. Install, that is for the standard stuff for however we install packages. We should probably be familiar from the trial project. Let's see. And while it is installing, I will point us at a a resource that we'll be using for looking at like basic environments in reinforcement learning. So this gymnasium library is kind of a go-to thing whenever for any kind of reinforcement learning research and just any kind of starter projects, as it includes a few toy environments that you can easily run on, whether you even have like hardware acceleration or you have GPUs, you don't have GPUs. And it provides a very simple framework of how do you interact with these environments. So let's see how this works. It's gym. So stable baselines uses gymnasium, so it will automatically have that available for you. And it also uses PyTorch, which we'll be using for this and later for implementing various kinds of algorithms.
For context, stable baseline is a library that implements a lot of different RL algorithms. So you don't need to worry about implementing them yourself. You can just start using them.
Yeah, we will still implement something for actual details, but this is something that you can kind of just plug and play apply, which is why we'll be using that for this little demo. So the first thing we want to do is we kind of want to set up some kind of algorithm to look at. Does any of these find like looks interesting? You want to see any one of these? Any preference? I know all of
So
these
the
look very
what's
fun.
the mountain car? Can you explain what it is? That looks curious.
Yeah, let's take a look at this guy. So there's some kind of flag on the hill, and there's a car on the bottom. So the problem with this is that the car doesn't have enough power to kind of just go right and reach the goal. So what the agent wants to learn, ideally, is kind of to swing up on that hill until it can finally reach the goal. And it shows us here this documentation of what can we expect from this. So the action space is discrete. So we have some kind of 3 actions available to us. And the observation state is a box. It's 2 boxes, which is not discrete. And judging by the fact that it's float 32, you can probably guess it's just a continuous, some kind of continuous vector observation. So in this case, it will probably be something like coordinate on x-axis and y. Or actually, I believe it's speed. It's position and speed for the mountain car. So how do we get this? Just do gymnasium make. So let's just do that. Oh, I imported this as gym, but so we'll do gym make. All right. Let's see. If you wanted to see any of this stuff that we see on the docs here about the environment, you can do this kind of, for example, how many actions do we have? We can access this action space in some ways. See that it's discrete, we can get a sample action from it. Sample it a few times, just example action. In some more advanced algorithms you might, or environments you might want to see, or what is the type of the observation that it has. We'll see one that will be more interesting to look at for that. But other than that, the gymnasium here provides some information about this stuff. So yeah, action space, what does it do? Accelerate to the left is 0, 1 don't accelerate, 2 is accelerate to the right, pretty straightforward. And yeah, they tell you a little bit about transition dynamics. What is the reward? So the reward here is, what is it? Starting velocity, okay, there's a state, this or that. The reward is to reach the flag as quickly as possible. As, yeah, we'll be getting a reward of -1 for each time step. So good. Let's do this. Render mode. render mode by default is set to RGB array. That's just meaning it will not be displayed to you like in this gameplay. And let's see. So now let's import some kind of algorithm for this. We're looking at one of the algorithms of Q learning. So let's import DQ learning, deep Q learning algorithm. That's actually the one that will be learning some kind of deep representations for us. Let's see. Import stable baselines. Import no, not PPO. Thank you. And how would you instantiate this? Is DQN. And yep, the Copilot is helping out here. But basically what you want to specify is this MLP policy. At some point we might discuss what this is, but basically it's just telling you that we want to use some kind of this DQN, these kind of stable basins. They have some standard kind of neural networks they use. MLP policy is this kind of one kind of architecture they use, and that they will be using under the hood. So later on, we will look at how to make your own policy for that. But stable baselines handles basically everything for us in that sense. Yeah, we just pass the environment to it. Verbose is just a flag to indicate that we want to see how the training progress is going when it will train. And yeah, now we can just learn for a little bit. Let's instantiate this thing. Another rip for a bit. And this little interface will kindly let us know what how our agent is doing. So it is telling us what's the average length of the episode. Usually it's 200 is probably the maximum length that it can go up to. So as you would expect with -1 reward, it's getting -200 because it's not getting to reward. Okay, and I assume that it finished quite fast because we only set 10,000 steps. And the funny thing about setting it to 10,000 steps with DQN particularly is that the defaults might not even train actually, but that's fine. We don't need it to train really. Let's see. How would you interact with the environment actually? Let's take a look. Let's interact with the environment for a few steps. For that, we'll want to reset our environment. What this reset returns is the first observation from the environment. I should probably have this can disable that, but that's fine. Action. What our DQN, the way this DQN works is we'll just call predict on this observation, and that will return us an action states. And interesting that it's returning as the states, but that's the interface of the DQN. And that's literally all the interaction for how you do this for Gymnasium. Very straightforward. You just call the step, and similarly to our little diagram here, you get back an observation reward and a few flags, some information about whether the environment has terminated at that step. So maybe it reached the goal that it will now finish, and whether it was truncated. I believe if it takes too long, and there is a condition at which there's a basically it will terminate, but for not for the reason of some kind of condition in the environment where it will usually stop by the rules, but due some other reasons. Maybe it's running too long or some kind of idea like that. Render is not needed necessarily in this case. Well, let's see if it will do anything really, because yeah, it won't. And we can print a few of these. Let's see what we get. Beautiful. So that's quite fast at some point. And for the mountain car, in order for this thing to solve it, we'll probably let it go for, we just train it for 10,000, 100,000 might not be sufficient, I want to say. But might work. We'll see, we'll see. Let's take a look at something else.
Bye.
Yeah.
By Max. We'll let it run for a bit and make another end for now. And one will close creatively. One good reason to kind of use not the collab is it's kind of a little bit harder to set up rendering. So in this case, this guy, for example, suggests me to use render, right? But it won't really render very well on collab unless you do additional configurations. In addition, there's like other good reasons to kind of try out local compute, especially if you have some kind of internal GPU, then you might want to consider that running that locally. So in this case, here I have a kind of local workstation with a GPU access. Let me just start this example. And here it will not train, but it will execute and show about what you can expect for evaluation, for example. So another just kind of way for you to see, you would see on the reward whether your algorithm is doing well, but with the kind of visualization, you can see in what way it fails if it does fail. In this case, we're looking at car pole environment, which is the idea is to balance a pole, and when it gets too low in either direction, it kind of just fails. So the only change to this code, to this whole thing that we've seen, was change the render mode to human. And I don't even know if we need render here, actually. Let's see. No, we don't. Yeah, that's a new gymnasium thing. Whenever you specify render mode human, it will just render within a step. So that's good. Let's see. For a more complicated example, see, that's not, other than these 5 simple things, let's see what else Gymnasium has to offer in terms of environments. We also have this box 2D thing, which provides you, instead of a set of vectors as states, it provides you with images for each of these. So for car racing, it would be, for example, trying to get this car to complete the lap as fast as possible. It's a little bit of a more complicated setup. And it can be either continuous or discrete in this case. So we have a little bit of a wider range of options. One thing to note, for deep Q learning in general, since we are trying to assign some kind of value to a state, then in general, this only works for discrete actions. So you'd only be able to apply to discrete environments, as we've seen with mountain card. But in general, you could try and see with most of these even continuous algorithms, probably like convert them to some degree to discrete if you wanted to. That won't be a necessity for you though, because there are quite simple extensions of DQN to continuous actions, as we'll see with Actor Critic. PPO is the policy base, which we won't be looking at most today. So at some point we'll look at that as well. For example, let's see. Soft actor critic is another one, which is value based, but well, I guess actor critic based, so that works out well. Yeah, I can let this guy run for a little bit. It's taking its time. Interesting. Okay, while it is taking its time, I've shown you in general how this interaction process works with this whole setup. So the thing that I would recommend you to do is to install locally, and that will kind of simplify for you the work with the reinforcement learning algorithms. Let's see. Okay, getting back here. It's taking its sweet time. I guess it's not printing the updates, which is fine. Okay. In the meantime, yeah, we've taken a look at Cartball. That's good. This one's actually quite fast to train, so we should be able to actually see it perform quite well if we just run it for a little bit. That is too fast. Let's give it a few more steps to collect. Oh yeah, I'm rendering it as human. It will take a little bit more time if you just render it. You don't want to render it as human during the training, because it will just render. It will be able to collect steps faster without rendering. So, okay, now it will read quite fast. Okay. And there we go. You already see some reward going up generally. So for card poll, you would be trying to balance the poll as long as possible. That's a kind of reverse strategy from what we had for mountain car. And yeah, just stay in place, balance the poll. Let's see, this has been 18,000 steps out of 100, so it will take like probably about a minute to finish. But it's already approaching 200, which 200 is probably max for it. Usually you take about 200 steps per environment. I don't know, it's more than that, which is nice. Three, okay. While we're waiting for this guy, the other thing that I wanted to kind of talk about was some of the basic tensor operations that we'll be looking at while actually implementing the DQM and like deep learning models for this. And not just deep learning models, but the various like utilities that we'll need for this. For example, we'll need to collect our experience somewhere. So how do we do that, and how do we actually train and update our model? Let's see. So yeah, let's just import a few things. First of all, we're using PyTorch, so we'll be importing Torch. Let's make some simple stuff. just multiply a few vectors. Let's see. Any prediction for what will happen here? Predictions. Vector multiplication. Yes. Should be quite straightforward, yes? And no problem with this so far.
Still no worries.
Oh, okay. Thank you. Is that better?
Could you also hide the text, chat box, and everything else?
Yes. It's funny. I actually don't see this chat box on my. Oh yeah, I do see it actually.
Oh, it's because it's sharing over there.
Yes. Thank you. Perfect. This is much better. Thank you. Yeah, it was actually probably very unreadable here. Yeah, it's very small. Okay. Yeah, no problem with this. I assume. You just multiply everything together. It's fine. That's all
So
right.
that's like an element-wise multiplication of the two tensors.
Exactly. Let's up this a little bit. Random things. And that. Okay. Let's just look at this guy. All right, so 2 by 2 matrix. Let's make 2 of these. Except okay, if I do this, what will happen? What's gonna happen? Should be quite straightforward as well. No problems with this. No problems. Okay. So this is element wise, right? This is not a matrix multiplication, this is just element wise. Matrix multiplication would be this. So this is just okay, some syntax. I guess that. I guess not. Oh yeah. Oh, let's see. I don't have the same data type. Right, because we specified integers. Why would it be? Yeah, we can implicitly just make it a float, or we can just say, and most of the time you probably want to just do this, just explicitly say that this is float 32 or something. And maybe you just want to have that on everything. But the errors are quite self-explanatory, so it should be okay with that. Yeah, let's see. Same matrix as identity. Matrix multiplication, no problem here. And another thing, who hear about broadcasting? Broadcasting anyone? Broadcasting. So that's one thing that's we can try to see how that works. In general, if you have, let's take a look at again at our A. So if we do that, it will broadcast, what we call. So we multiply every row in this case by the vector. And that is done somewhat automatically. If we do this, will it complain? It will not complain, it will do the same thing. So it will, so to speak, broadcast and apply all of the operations to all of the dimensions, instances in the dimensions that are before the last dimension. What if we do it for 2? Will it figure out to do it for other dimensions? No, it won't, because it is trying to do this on the last one. But if you wanted to do broadcasting on any like number of dimensions that you have in mind, and that is probably the best kind of broadcasting, where you're specifying what exactly you want to do, where exactly you want to broadcast, and you don't deal with any surprises later down. Because if you, for example, have 2 dimensions that are 2-dimensional, right? And you have some kind of value that you want to multiply for each value on one of the dimensions, then you might want to, let's see, I guess it will apply to anything anyway, so that's fine. That will actually work, right? So in that case, in order to do broadcasting, you will need to specify these additional 1 dimensions. This is specifying this shape dimension, and that is how that works. If we wanted to do, for example, a cross product, that's called, right? Whenever you want to get a matrix from multiplying 2 vectors. Let's do that. Any ideas how we would make cross product? Well, I guess it's helping me in this. Will we get matrix from this? No? Yes? Probably not. Yeah, because we will, because previously defined A is matrix. Oh, cool. Interesting. Okay. Yeah, no, we want broadcasting. And there we go. If we want to do some kind of thing like that. Why is this interesting? Why is it important? We will be working with different dimensions quite a bit. There's a general convention that for whenever we do updates or we calculate the updates for any kind of network, we will be aggregating data for updates into batches, random batches, and that will be done in the first dimension. And we'll usually want to do various kinds of stuff with that information. So for example, let's briefly assign this thing. What we can do is we can aggregate in various ways. First, we can just calculate some, but we can also aggregate along some kind of dimensions, and often in like calculating loss or calculating any kind of values that will be relevant to us here, we will be calculating along this, aggregating along this 0 dimension for kind of all of the batches, like getting an average value for the batch. So this is kind of to get us a little bit comfortable with what we'll be doing in a little bit. Okay. Let's check out our thing here. Wonderful. Oh yeah, so our pendulum has reached 500 reward in this, probably quite a while back, but it's just another example. I wish I could increase the size of that, but yeah, that's pretty infeasible, is it? Oh, you'll have to believe me that this trains well, and you can train it on your laptop and whatnot. So that's a good thing. Well, I guess the last thing to mention here is that in general, if you have access to GPU resources, you'll get quite a significant boost in machine learning in general. Let's just see. We'll do some kind of big matrices. B. And if we time this whole thing, and just introduce some timing things. It's not a stretch to, not a hard thing to believe that it will take a small, less time on GPU, but still. Right. Let's see how much it will take us. Oh, it takes quite a bit to even just initialize. Yep. That takes quite a bit. It's not affecting it. I think while I run this, I'll just run this. It will take. Oh yeah, it can't really. Okay, beautiful. What is this? No NVIDIA driver found because we are connected. We're not using GPU by default. And let's see. You need to change that settings here. Change runtime type. T4 GPU. Save. Okay, let's see if we this now. We'll need to re-import everything basically. There it is. And there we go. That the other one took what, 39 seconds. This one took 45. And granted, I'm cheating here a little bit because we will still need to grab the memory back from CUDA to CPU. But in general, since all of our updates will be happening on the GPU side already, we won't be doing that travel a lot. So do use GPU. GPU is faster. Great insight. Okay. And yeah, that's basically all I have on what I wanted to show you in prep for building some DQNs and DQ networks next time. So we will be well equipped for it. Great.